All right, are we ready? Okay. Our second speaker is Margus Veanes, who's going to tell us about derivative-based, non-backtracking, real-world regex matching with backtracking semantics. Take it away.
Thank you for attending this session. And let me start by saying that this is a work that spans roughly 4 years. It's a collaboration between Microsoft Research and Microsoft Azure and Developer Division more recently. So it started with the work we did with Azure, so what I will briefly mention on the next slide. Then I'll talk a little bit about the history, but cannot go too much into the details. Let me start by giving sort of a high-level overview what kind of matching algorithms exist and what are the trade-offs between them. So on one hand, you can build very efficient matching, very fast matching with backtracking. It's very general. But you can also use NFAs, which require more pre-processing, but avoid some problems with backtracking, such as exponential behaviors, and provide more linearity in the matching process. So examples would be Thompson's algorithm that most well-known regular expression matchers is based on. Then there is Glushkov's algorithm that Hyperscan is based on. And there are also Antimirov derivatives. And then on the DFA side, of course, you can on-the-fly determinize NFAs to DFAs that most of the above matchers do, and then the fallback strategies fall back on NFAs. But there is also a direct approach by using Brzozowski derivatives with the SRM tool that is the predecessor of the work that I'm going to present here. Then there is, of course, derivatives that is somehow a middle ground. Derivatives provide a kind of incremental way of creating an automaton one step at a time, and they've been studied in the functional program community since around 15 years ago by Fisher and Owens, who point out that usually when you use derivatives, you get a small state space. They tend to minimize the number of states. Then there's also studies about POSIX semantics, so finding a matchend that is mostly related to the work here. So what we present here is a new backend for .NET, which provides an algorithm that provides linear matching and extends, so it's released since November last year in .NET 7. So what does the new non-backtracking engine provide? So the main features are it's input linear with respect to the input, essentially. There is no backtracking. It supports most regular features, including anchors, captures, has backtracking semantics, which is also named PCRE semantics, and is compatible, most importantly, with the other backends. Otherwise, a user might have a very weird experience if you swap one backend against another, but you get different semantics in the matching algorithm, which is not very desirable. Things that are not supported are non-regular features like back references and balancing groups. Lookarounds are not supported currently, but can be supported, but they contradict input linearity. So the seamlessness comes with a price here. So it's theoretically and algorithmically easy to support, but then providing input linear matching is then a different angle, which cannot be easily supported. And conditionals are not supported. So here is the quick abstract syntax overview of what these regular expressions are. And unlike the previous talk, I prefer the bar symbol for OR. And also important fact here is that alternation, that OR, is not unordered. So it's not commutative. It's associative, it's idempotent, but it's not commutative. And the last expression denotes loops, where M is the lower bound, N is the upper bound, and B is a Boolean that indicates whether the loop is lazy or eager. So in the last example, for example, the very initial dot star is lazy. It means try to minimize the number of characters before you try to match she or he. And I will be using the word border in some examples, so I'm pointing that out here. So when should one use non-backtracking? So there is an excellent study by James Davis, who actually visited during that time in 2018. He visited Arise. I think he was doing an internship there. And he has a really excellent study. It goes very deep into all the aspects of, looks at many, many different applications of regular expressions and studies REDOS in those contexts. So REDOS stands for Regular Expression Denial of Service. When the regex has many alternations is another context where you might want to use non-backtracking. But in general, I would want to claim there is no best engine. Every backend has its own purpose. So in total, there are 4 backends in .NET. The non-backtracking one that I'm talking about here, then there is none, which is essentially backtracking but interpreted, and then there is a compiled version of it that is faster, and there is also a new source generated, essentially backtracking standalone source that is also in .NET. That is a further optimized version of compiled code. So what is new in the work? There is a new theory of derivatives based on locations instead of characters. There is a notion of derivative-based backtracking simulation without actually backtracking. So backtracking is encoded into the derivatives themselves. There is a rather elaborate regex rewrite system that is implemented as part of the system, so it actually is practical and terminates. And finally, there is an alphabet compression algorithm, actually based on BDDs, that allows dealing with very large alphabets, in this case Unicode. And finally, let me also mention this, that this is the first industrial implementation of input linear matching that has a proof of correctness. The prior tools essentially ignore a lot of side issues, sort of like anchors, because anchors don't have classical semantics. So let me start by just giving you a very quick view of what I mean by compression here. So usually in other tools, compression is based on, say, for example, in RE2, it would be based on UTF-8 encoding. So there are 2 phases. You first pass the input string as a UTF-8 string, but here it's not possible because characters are UTF-16, or actually not UTF-16, but 16-bit characters. There is no direct UTF-16 encoding meant. So we're dealing with Unicode. And the alphabet is too large for the elements to be dealt by one. So what we do first is divide them into Boolean combinations of character classes that actually matter. These would be regions in a Venn diagram. So in this case, there are just 2 that I note here by 0 and 1. Anchors add some complexity to derivatives, so you can't take a continuation of a regex just based on the current character, but you need to know the context. So the context is essentially the location where you're at. And the location is between 2 characters. Essentially, you can think of it as the prefix and the suffix of a string. You're at that point. And so these are indicated by S0, S1, and so forth. So for example, in this string, where is he, you have 2 occurrences of he. And in the first location, S1, the character H does not start the word. In the next position, S9, where it occurs, it does start the word. And this affects, for example, the outcome of matching, for example, for a regex that says word border followed by HE, which means H has to start a new word. So location derivatives are kind of an extended version of derivatives, and they introduce a state machine lazily during matching. And it's important to cache those states. So for example, here you would start with the regex I showed earlier, and you would build up a state machine, which then is cached. And at this point, where I've seen the first 3 characters, we don't actually need to compute the derivatives anymore because they're already cached and reuse the old results. So you essentially just read the state machine directly. So what happens often is the derivatives are very quickly computed and create a state machine that is then used over and over again. And so one might think that representation of derivatives is a huge cost. In fact, in practice, it is not. Whereas the acceptance condition is not classical, it is based on what follows as the next symbol, as in that current state marks. There are some fundamental classic laws that fail for these for regular expressions with anchors, and these 2 would be good examples. So you can take two regular expressions, concatenate them, take the language that is empty, like the R below, because if you take A followed by a word border, followed by A, it's infeasible. Word border doesn't exist between two word characters. So it is empty, whereas, of course, the R by itself is not empty. It contains at least A. So location-based derivatives, as I already said, alternation is not commutative, so it kind of creates an interesting variant of derivatives where you need to create the order of choices as you read and create derivatives, and the key operation is concatenation that essentially creates new choice points. I'm not going to go over these details, but even in this already examples, we have all the cases I talked about explicitly shown. The definition of finding an end of a match is essentially a iterative procedure. It's a tail recursive procedure that just walks and creates the derivatives on the fly and tries to find the point where it matches. So this is essentially the implementation in a nutshell, of course, with many optimizations missing. You fail means match failure, and is match if there exists no match. Let me skip ahead a few slides because I realize I'm running out of time. There are alternation is not commutative. There is an aspect of pruning. Pruning means the regular expression is pruned in order to cut away those choice points that a backtracking would not make. And the match, in a nutshell, is something like this. This is exactly what it is. So you start from a position S0. You mark a derivative as being in backtracking mode, and then you find an endpoint, and from that endpoint Y, you walk back to find the start point. So it's two phases, forwards and backwards. And yeah, in this case, in the example, you would find the first he because the regex demands that the he is bounded by non-word borders. That's another anchor. So main theorist, correctness theorem, I only wanted to state it here, but highlight an aspect that is, we actually formalize what backtracking semantics means in the paper and then prove its correctness with respect to the derivatives. Integration into .NET regex library is several years of work. It supports all public APIs. There are many shared optimizations, so it's very, very tightly integrated. And there are thousands of tests that validate that all the backends produce the same results. Some crucial aspects of implementation are caching, very important rewrite rules, for example, idempotence for non-commutative alternation, and then fallback mode to NFA mode when you run out of state. So essentially, DFA versus NFA is a time-space trade-off. There are also some tricky aspects I want to go in, but I don't have time. First one is that regular expressions are not referentially transparent. You can take two regular expressions and put them in a context of ignoring case, and they are actually not the same thing anymore. Many people don't know that. But that comes from a very weird standard from Unicode, which has to do with ignore case. There are also many problems with ignoring culture dependency, and there are also, anyways. Let me jump to some comparisons. So benchmarks. So what we came up with, so what we realized is through these benchmarks is that non-backtracking kind of what sort of these other papers predicted, that derivatives give you a nice small state space compared to, say, DFAs and NFAs, seems to also be true here. So there are a least amount of outliers. So for example, otherwise, Rust, which is effectively a version of RA2, it would be a clear winner if it wouldn't be for this one bad regex. We have internal case studies. This one is an internal case study of word phrase regex matching that use extensive use of word anchors and a lot of alternations where non-backtracking clearly pays off compared to a compiled mode. And finally, the benchmark CredScan that is used in production for several years already, initially by SRM, now they're moving over to .NET 7, shows the advantage of non-backtracking, actually compiled became much faster during the last releases, but it still has benefit over. So non-backtracking still has benefit, and particularly avoids the outliers that can be very painful. And that's it. Thank you for your attention, and please try out the source and build your own project on top of it. It's all open source that I talked about. You can all check it out and see how it works in reality. Thank you.
Great, thank you. Questions from the audience? Oh, yeah. Name and affiliation.
Yeah, Gary Tan from Penn State. So in the original derivatives, my understanding is you can do termination proof to prove the derivative algorithm always terminates to generate a DFA. And in your new derivatives, have you thought about the termination proof?
Yes, it does terminate. The reason is that the alternation is still associative and idempotent. Even though you may have different orders, you can theoretically get factorially more cases, like different orders. But the original proof of Grozovsky is based on the fact that it's commutative, associative, and idempotent. But you can drop commutativity from that.
Okay, sounds good.
So I have a question. So in your paper, can you go back to the performance slide? You had, in the section about the performance, you had talked about, the against compiled and none.
Ah.
Sorry. So you had talked about adding optimizations to the non-backtracking to reduce the startup overhead. And I was, the initialization overhead, I think this was sort of one reason why I was losing against none on small examples.
That's right.
And I was just curious, since those already run fast, how important do you think that is?
So the question is about the cost of initialization and how that affects the overall performance. I would say for very small examples, you would still prefer none, because if you don't have any sort of risk because there is very, very low overhead with backtracking, right? So the overhead with compiled comes, you have to at least compile it. With non-backtracking, the additional overhead is the min-termization. Essentially, you create the BDDs. So there is a BDD algebra. And initially, essentially we're working with symbolic automata. The transitions of the automata are predicates, and there are 3 layers. First, we start with BDDs, and then we convert that into bit vectors, where the bits are essentially single bits, 1 per min-term. So it's very, very efficient to work with integers and integer encodings of predicates. And that, of course, costs. That's the initial cost. And for very small examples, it doesn't pay off. For large examples, when you're all over gigabytes of data, like CredScan does daily, and where you have fixed regexes that you never recompile, pays off big time.
Thank you very much. Let's thank Margus again. We'll get our next speaker up here.